Hello guys, today I'm going to talk about optimization problems. All optimization is applying the ideas of calculus and the derivative to some word problems in order to help me find a maximum or a minimum value. And again, we learned about finding about extrema earlier in this chapter. Alright, so here are your guidelines for solving a maximum and minimum problem. In other words, optimizing something, right? You can, if you want, you can pause this at your leisure and read through these, okay? Now, let's take a look at a problem where we can use optimization. All right, so take a look at this. It says, a metal box is to be created from a flat rectangular piece of sheet metal with dimensions of 20 inches by 30 inches by cutting out squares from each corner and folding up the leftover tabs. What are the dimensions that will maximize or minimize the volume of the box? Okay, so the first thing I want to take a look at is what I know and what I don't know. Well, let's see. I know that I have a rectangular sheet of metal here, right? Where the dimensions are, say, 20 inches by 30 inches. Now, what I'm going to do is I'm going to cut out little square tabs like this from each corner. Okay, and I want to cut these square tabs out. If these squares disappear, right, what I get is a shape that looks like this, correct? If I cut these squares out, I get this, right? Now, what I'll do is, I'll have these little leftover tabs here, 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 and here, that I'll then fold up to make a box that would resemble something like this. All right? So that's what I want to do. Can everybody envision this? This red base right here would be the bottom of this box. So if I drew in like this back wall here, that bottom would be like right here. And each of these tabs right here would be, again, like the front, the sides, and the back of the box, right? And there would be no top to the box. All right? So that's what I want to do. I want to try and create this rectangular prism or box right here by cutting out these little squares, right? Now, how much should I cut out? That's the question. Well, since it's going to be a square, I know that if I cut out x inches from this side, I have to cut out x inches from this side. X and x, x and x, x and x, correct? By doing that, that is what will allow me to fold up the sides of this box, the sides of this metal to create the box, right? All right, so that's what's going on. Now, I know to maximize my volume, to find the volume of a box, the first thing I want to do, if I'm trying to maximize the volume, I first have to think about how you find the volume of a box like this. Well, isn't the volume of a box like this just length times width times height? All right? This is what I want to maximize right here. I want to get the biggest volume I can. Now, the only problem is I've got three different variables here. I've got an L, a W, and an H. That's no good. I have to rewrite this in terms of just one variable. Well, that's where my diagram is going to help me do this. I know that if I cut x inches off the right and x inches off the left, well, since this whole thing used to be 20, shouldn't what's left just be 20 minus 2x? And wouldn't that be, say, the front edge of this box, or you want to call it the length? Wouldn't that be 20 minus 2x? Likewise, if I cut x inches off the bottom and x inches off the top, and this used to be 30 inches in length, shouldn't what's left be just 30 minus 2x now? So that would be this side coming back here, 30 minus 2x. And then lastly, when I fold up these this length of x, to make all these different walls of my box, wouldn't the height of my box just be x? Can everybody see that? So using my diagram, I can say that the volume of this box in terms of x would just be, well, the length would be 20 minus 2x. The width would be 30 minus 2x. And the height is just x. Well, according to this, if I took this equation right here, and I wanted to find its maximum and minimum values, I could use calculus. Now, the first thing I want to do before I do that, I want to talk about the domain of this guy. All right? The domain is the values that I'm allowed to use for x. Well, what is x? In this problem, isn't x how much I'm cutting off each each side of the box, right? So I'm going to cut X inches off the right, X inches off the left. Well, if the whole bottom is 20 inches across, what's the maximum that I could cut off? Does it make sense why I couldn't cut off 10 inches? Because if I cut off 10 inches from each side, you wouldn't have any bottom left, right? Likewise, if I was going this, cutting off from here and here, the most I could cut off would be 15 from each side. But wait a minute, if I cut 15 off of this side and 15 off this side, I'd have to cut 15 off of this side and this side. But that's not possible because I only have 20 inches total. So how could you cut 15 off of each side? So does it make sense that the maximum value of X would have to be 10 inches that I could cut off? What's the minimum amount? Well, does it make sense that I have to cut something off of each side, or else I wouldn't be able to create a box. So my domain on this guy would have to be from 0 inches that I cut off to a maximum of 10 inches, with parentheses, meaning I have to cut something off. So I can't cut 0 off, and I can't cut 10 off, because then I would have nothing left on the bottom. Okay? So that's my domain. All right, at this point now, I'm going to take the derivative of this function, and I'm going to try and find the maximum value created within the domain of 0 to 10. All right? Well, to do that, the first thing I'm going to do is I'm going to make this into just one standard form polynomial. Okay, by just multiplying these three terms out, these three factors out, I get this new equation, which will be a little bit easier for me to take the derivative of. If I take the derivative, the derivative of this would equal 600 minus 200x plus 12x squared, correct? Now, I want to, again, to find the maximum minimum values. I know that happens at critical values, so I'm going to now plug this 0 in for the derivative and solve for x in this equation. All right? I'm going to go ahead and do that. Okay, when I solve this this quadratic, I use a quadratic formula to solve, I get these two values right here. Okay? So those are my critical values. Now, of course, to see if they're maxes or mins and whatnot, which would produce a bigger one, a bigger value for the function, I'm now going to place these numbers on my number line. So I put, let's see here, 3.924 here, and I put 12.743 here. And I'm going to find values in each interval that are inside the domain of my function and see which one produces a max or min. So the first thing I'm going to do, I'm going to choose the number 1. So plugging 1 into my derivative, which was right here, I would get the derivative at 1 would equal 600 minus 200 times 1 plus 12 times 1, right? Now again, all I care about is if that's a positive value or a negative value. Well, if I think about this, I think I would get a positive value here, right? Now plugging the number in between 3.924 and 12.743, I'm going to pick a number in here that's in between there. I'm going to pick, I don't know, say 5, right? Putting in 5, I get 600 minus 200 times 5 plus 12 times 5 squared, right? Actually, that's squared there, right? So this one's going to be a little bit more mass. So 600 minus 1,000 plus, let's see here, that's 25 times 12 is 300, all right? So I get, what's this, 900 minus 1,000. So that's equal to negative 100. So I know that I get a negative value for my derivative there. And plug in a number that's greater than 12 in for x. If I plug in, say, 13 for x, again, it's got to be in the domain. Oh, wait a minute. I don't even need to check the 13, right? Because I know that my domain can't go past 10, correct? So the reality is, this value right here, I know that he's outside my domain, so how could I have this length of 12.743 cut out from each side, right? So it seems like this should be my value that will maximize it. Well, now looking at my sign chart, would you agree, I'm going to the left of 3.92, I'm going up because I got a positive derivative. To the right, I'm going down because I got a negative derivative. That point must be a local max, right? So according to this, I think that x should equal 3.924. Well, again, if x is how much I'm cutting off at each side, I can plug that 3.924 in for this x here and this x here and find out the length and the width that would also find those maximum and minimum values. All right, guys, let's take a look at one more example here for optimization. On this one, this is pretty straightforward. It's just an algebra problem. It says find the points on the graph of y equals 4 minus x squared that is closest to the point 0, 2. Now, if you think about this, and again, you can use your graphic calculator to look at this more in depth, but what I'm looking at here is I'm looking at a parabola that's frowning and that has a vertex of 0, 4. So it looks something like this. And I want to find all the points that could be on this graph that would be closest to this point, say 0, 2 right here, right? Now, would that point be straight up? Maybe it might be diagonally this way, might be diagonally that way. Where would be the closest point on this graph to 0, 2? All right. All right. So what I'm trying to optimize is a distance. I'm trying to find the shortest distance between a point on the graph and this point 0, 2. Well, then what I want to do is I want to use my distance formula from geometry. I know that the distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And again, that's the Pythagorean theorem applied to 2 points, right? Well, let's see. I can plug in. I know one of the points is 0, 2. So I can plug in the 0 for x1 and the 2 for y1. So I get, let's see here, x2 minus 0 squared plus y2 minus 2 squared, right? Now the reality is, since I no longer have two x's and y's, I can just go ahead and rewrite this as just a single x that's b squared, and then a single y minus 2b squared. I don't need to use the subscripts anymore to name them because, again, there's only one point involved in this problem. All right? Okay, well, now here's my issue. I've got two variables in this right side. I've got an x and a y. So my distance is written in terms of two variables, not one variable. But wait a minute. If I wanted to use substitution, would you agree my initial equation of 4 minus x squared, isn't that what y equals? So couldn't I use substitution to rewrite this as just x squared plus, instead of this y, I'm going to rewrite that as 4 minus x squared minus 2 squared, right? Does everyone see how I got that? And now I have this in terms of just the letter x. Now, just simplifying a little bit, I get square root of x squared plus, let's see, that would be let's see here, that would be 2 minus x squared, is that correct? Squared, right? Multiplying this out, I would get the square root of x squared plus, that would be 4 minus 4x squared plus x to the fourth, right? Combining like terms, I get my distance to be, let's see here, x to the fourth minus 3x squared plus 4. And now I can find the derivative of this, right? So my derivative of the distance in terms of x would equal, well, let's see, take the square root of that, wouldn't just be the derivative of the inside, it would be 4x cubed minus 6x over 2 times the initial square root of x to the fourth minus 3x squared plus 4, right? Now, to find the critical values, I'm going to set this denominator, I'm going to set the numerator equal to 0, and get to 0 equals 4x cubed minus 6x squared, minus 6x. Solving, I can factor out an x, and I get x, parentheses 4x squared minus 6. So I get x equals 0 from him, and from here I would get x equals, let's see, well, I'm going to x squared equals 6 fourths. So square rooting both sides, I would get x equals just positive negative square root of 6 over 2, right? And so I've got three values here. I've got 0, I've got the positive square root of 6 over 2, and I've got the negative square root of 6 over 2. All right? So now testing these values, I got to test to the left, in between, and to the right. Okay? Well, let's see here. The square root of 6 would have to be 2 point something. So I know I could safely pick, say, just to test in the derivative, I could test, say, negative 10 if I wanted to. If I plug a negative 10 in here and a negative 10 in here, and a negative 10 here and a negative 10 in here, what value would I get? All right, so plugging in negative 10, I would get, let's see here, this negative 10 would be like negative 4,000 plus, let's see, 60. Well, that's definitely going to be a negative on the top of here. this bottom would definitely be a positive on the bottom here, because when you square root a number, it's always positive. Times 2 is positive. So I know if I plug a negative 10 in, I'm going to get a negative, right? So on my sign chart here, I know to the left of negative square root of 6 over 2, I'm going to get a negative number, right? Now I got to go back and I've got to plug a number in the interval between negative square root of 6 over 2 and 0, right? So I'm going to pick negative 1. If I pick negative 1 and I put it in here, let's see here, I would get negative 4 plus 6 is 2, so that's positive on the top. In the denominator, I know I always have to get a negative number, right? Right? And so, let's see here, positive divided by a negative, again, is negative, right? So according to this, I would get another negative value, right? I'm sorry, I'm wrong. That bottom has to be positive. I'm a bozo. The positive divided by positive is positive. So I know that interval I get a positive value. All right, plugging in a 1 again. I'm going to plug a 1 in this time. Let's see here. In the numerator, I would get 4 minus 6 is negative over a positive, because the bottom's always got to be positive to the square root, so it'll be a negative again, right? And then to the right of square root of 6 over 2, if I plug a number in, more than the square root of 6 over 2, well, again, I think that would be like square root of 6 would be 2 point something, divided by 2 is 1, so I'm going to pick a nice safe number like 3. How about 3? Actually, now let's pick a nice big number like 10. If I plug a 10 in, again, I would get 4,000, plugging in for the first term on the top. I get 60, 4,000 minus 60 would be positive on the top. I would get negative on the positive on the bottom, so that must be positive, correct? So this is my sign chart. So let's see here. I'm going, for this one, I'm going down on this side, up on this side. That's a minimum. On this one, I'm going up on this side, down on this side. That is a maximum. And on this one, I would get down on this side and up on this side, so that would be a minimum, right? So I get 2 minimum values, right? I would be closest to the point 0, 2 at positive negative square root of 6 over 2, right? Which kind of makes sense, because if you think about it, doesn't this graph have symmetry about the y-axis? Right, and so if I had a closer point, a point closest on the right side of the y-axis here, there must be a mirror point on this left side, right? And that would occur at, again, the square root of 6 over 2 negative and the square root of 6 over 2 positive, right? Okay, and that's optimization. I hope this helps. Bye.